Start with linear regression, one of the foundational models in machine learning. The main goal of linear regression is to minimize the mean squared error, or MSE. This means the model tries to make the vertical distances between the actual values and the predicted values as small as possible. For example, Airbnb uses linear regression to estimate rental prices for millions of properties, taking into account factors like square footage and booking trends. By minimizing MSE, the model provides the most accurate baseline rental values. This approach is widely used because it's mathematically straightforward and interpretable, making it a go-to method for many real-world regression problems. Ordinary least squares, or OLS, linear regression relies on several key assumptions. First, it assumes a linear relationship between features and the target. Second, the errors should be independent of each other. Third, the variance of errors, known as homoscedasticity, should be constant across all levels of the independent variables. Lastly, the errors should be normally distributed. If these assumptions are violated, the model's predictions and confidence intervals may become unreliable. For instance, if a real estate model's errors grow with higher-priced homes, it violates homoscedasticity, making its predictions less trustworthy. Multicollinearity occurs when two or more independent features in a linear model are highly correlated. This can make the model's coefficient estimates unstable and destroy the interpretability of each feature's effect. For example, if an insurance model includes both vehicle weight in pounds and in kilograms, these features provide the same information. The model will struggle to assign stable weights, leading to unreliable prediction. Detecting and addressing multicollinearity is crucial for building robust linear models, especially when interpretability is important. Using linear regression for binary classification is not recommended. Linear regression predicts continuous values which can range from negative to positive infinity. Probabilities, on the other hand, must be between 0 and 1. Additionally, linear regression is sensitive to outliers, which can shift the decision boundary and lead to misclassifications. For example, if a bank uses linear regression to classify transactions as fraud or clean, a single large transaction can skew the model, causing many fraudulent transactions to be misclassified. This is why specialized classification models are preferred for such tasks. Logistic regression transforms its output into a probability using the sigmoid or logit function. This function takes any real number and squashes it into a value between 0 and 1, making it perfect for classification tasks. For instance, Stripe uses logistic regression to assess the risk of transactions. The model passes risk signals through a sigmoid layer, outputting a probability like 0.87, which means there's an 87% chance the transaction is fraudulent. This transformation is what enables logistic regression to act as a classifier. Logistic regression uses binary cross-entropy loss, also known as log loss, instead of mean squared error. The reason is that combining the nonlinear sigmoid function with MSE creates a nonconvex optimization surface, making gradient descent unreliable. Log loss, on the other hand, penalizes confident but incorrect predictions much more heavily. For example, PayPal's risk engine uses log loss to ensure that assigning a high probability to a transaction that turns out to be fraudulent is penalized, improving the model's reliability in high-stakes scenarios. K-nearest neighbors, or KNN, algorithm is a nonparametric instance-based learner. When classifying a new data point, KNN calculates the distance between this point and all training examples, then selects the K closest neighbors. The majority vote among these neighbors determines the prediction. For example, a telecom company uses KNN to decide which cell tower should handle a new user's connection by finding the 3 closest towers. This simple yet powerful approach makes KNN a popular choice for classification and regression tasks. Adjusting the value of K in a KNN model directly impacts the bias variance trade-off. A low K, such as K equals 1, creates a highly complex and jagged decision boundary, resulting in low bias but high variance, meaning the model overfits to noise. A high K blends data distributions, leading to low variance but high bias, which can cause underfitting. For example, in a loan default risk model, setting K equals 1 means decisions are based on just one neighbor, which could be an outlier, making the model's predictions unstable. Feature scaling is essential before running a KNN model because KNN relies on geometric distance calculations. If one feature has a much larger range than another, it will dominate the distance metric, making other features irrelevant. For example, in a fitness app, if weight is measured in grams and age in years, the age difference becomes negligible compared to weight, skewing the results. Proper feature scaling ensures that all features contribute equally to the distance calculation, improving the model's accuracy. Decision trees determine the best split point for data features by evaluating every possible split across all features to maximize impurity reduction. For classification, they minimize Gini impurity or entropy, while for regression they minimize child node variance, often measured by MSE. For example, a streaming service might split users based on how many days they were active in the first week, finding the split that best separates active from inactive users. This process helps the tree make more accurate predictions. Gini impurity measures the likelihood of a randomly chosen element being incorrectly labeled if it were classified according to the label distribution in a subset. The formula is Gini equals 1 minus the sum of the squared probabilities for each class. Gini impurity ranges from 0, which means perfect purity, to 0.5, which represents a perfect 50-50 split in a binary classification. For example, a node with only failed transactions has a Gini impurity of 0, while a node with half failed and half successful transactions has a Gini impurity of 0.5. Constrained decision trees are prone to overfitting, because they can split until each training row is isolated in its own leaf node, essentially memorizing the noise in the data. To prevent this, techniques like pruning or setting constraints such as maximum depth, minimum samples per split, and minimum samples per leaf are used. For example, a marketing model without depth limits might create a rule for a single user based on their exact timestamp, which won't generalize to new customers. There are three main types of gradient descent: batch, stochastic, and mini-batch. Batch gradient descent computes gradients using the entire dataset, which is slow and memory intensive. Stochastic gradient descent, or SGD, updates weights using one random data point at a time, making it fast but volatile. Mini-batch gradient descent strikes a balance by processing small batches, like 32 or 128 rows at once. For example, Pinterest trains image classifiers using mini-batch gradient descent to optimize speed and stability on large datasets. In logistic regression, the odds ratio represents the probability of an event happening divided by the probability of it not happening. The log odds is simply the natural logarithm of the odds ratio. Logistic regression fits a linear plane to the log odds, allowing for straightforward interpretation. For example, in clinical health models, an odds ratio of 1.2 for smoking means smokers are 1.2 times more likely to develop heart disease than non-smokers, holding other factors constant. Standard scikit-learn decision trees require complete numeric matrices and do not handle missing features natively. The industry standard is to use imputation transformers to fill in missing values, or to use advanced frameworks like XGBoost or LightGBM, which can route missing values to an optimal default node during training. For example, a flight booking platform with missing baggage weight data can use XGBoost to automatically learn the best way to handle these missing values, improving model performance. Parametric models assume a fixed functional structure and are defined by a set number of parameters like linear regression. Non-parametric models such as KNN and decision trees do not assume a fixed shape and can grow in complexity as more data is added. For example, a sales forecasting model using linear regression assumes a constant growth rate, while a decision tree can adapt to sudden spikes or drops in sales, making it more flexible for unpredictable patterns. Scikit-learn-fit is used to calculate statistical metrics from a dataset such as the mean and variance. Transform then applies these metrics to scale or alter the data. Fit-transform combines both steps for efficiency, applying them sequentially on the same dataset. For example, when normalizing user transaction histories, you use fit-transform on the training set to learn and apply the scaling, and then only transform on the test set to avoid data leakage. Running fit-transform on your test dataset is a critical mistake. It recalculates scaling parameters based on the test set, leaking information from the test data into your evaluation process. This distorts your performance metrics and can cause the model to underperform in production. For example, if the test set contains a few extremely high-value users, fit-transform will rescale the test data using a skewed mean, masking the model's true performance on typical data. Random state parameter in scikit-learn acts as a seed for the internal pseudorandom number generator. This ensures that random processes, such as splitting datasets or shuffling data, produce identical and reproducible results across different runs. For example, a data science team at Tesla can set random state equals 42 so that every engineer gets the same validation scores when running the same script, making collaboration and debugging much easier. Handling high cardinality categorical features, like zip codes in linear models, can be challenging. One-hot encoding creates thousands of sparse columns, leading to multicollinearity in the dummy variable trap. Instead, target encoding replaces each zip code with the mean target value for that zip code or groups them into larger regions. For example, an insurance model might use the average claim payout for each zip code, keeping the feature matrix dense and predictive. Mean squared error, or MSE, is a fundamental metric in regression tasks. It calculates the average of the squared differences between actual and predicted values. Squaring the errors penalizes larger mistakes more heavily, encouraging the model to focus on minimizing big errors. This makes MSE a sensitive and effective loss function for many regression problems, ensuring that predictions are as close as possible to the real value. Linearity is a core assumption in linear regression models. It means that the relationship between the input features and the target variable is expected to be linear. If this assumption is not met, the model's predictions may be biased or inaccurate. Detecting nonlinearity early allows data scientists to choose more appropriate models or transform features to better fit the linear assumption. Homoscedasticity refers to the assumption that the variance of errors remains constant across all levels of the independent variables. If the variance changes, the model's confidence intervals and statistical tests become unreliable. For example, if prediction errors increase with higher values of the target variable, the model may need to be adjusted or a different modeling approach considered. Another key assumption in OLS regression is that the errors are normally distributed. This is important for making valid inferences about the model parameters and for constructing accurate confidence intervals. If the errors are not normal, the model's statistical conclusions may be invalid, and alternative modeling strategies might be necessary. Dummy variable trap occurs when one-hot encoding is used for categorical variables, creating multicollinearity among the new columns. This can make the model's coefficients unstable and the results difficult to interpret. To avoid this, one column is typically dropped or alternative encoding methods like target encoding are used, especially for high cardinality features. Sigmoid function is central to logistic regression. It takes any real-valued input and outputs a value between 0 and 1, which can be interpreted as a probability. This smooth, S-shaped curve makes it ideal for binary classification tasks, allowing the model to output probabilities for each class rather than just hard labels. Cross-entropy loss, or log loss, is used in logistic regression to measure the performance of a classification model. It penalizes predictions that are both confident and wrong much more than less confident mistakes. This property helps models avoid overconfidence and encourages more calibrated probability estimates, which is crucial in applications like fraud detection. KNN is known as an instance-based or lazy learner because it does not build a model during training. Instead, it stores all the training data and makes predictions by comparing new data points to the stored examples. This makes KNN simple to implement but potentially slow at prediction time, especially with large datasets. KNN relies on distance metrics such as Euclidean distance to determine the similarity between data points. The choice of distance metric can significantly impact the model's performance, especially when features are on different scales. That's why feature scaling is so important in KNN models. In KNN classification, the prediction for a new data point is determined by a majority vote among its K nearest neighbors. This simple approach makes KNN easy to understand and interpret, but it also means that the model can be sensitive to noise and outliers in the training data. Bias variance trade-off is a fundamental concept in machine learning. Models with high bias are too simple and underfit the data, while models with high variance are too complex and overfit to noise. Adjusting parameters like K in KNN or tree depth in decision trees helps find the right balance for optimal performance. Common feature scaling techniques include min-max scaling and standardization. Min-max scaling rescales features to a fixed range, usually 0 to 1, while standardization transforms features to have 0 mean and unit variance. Choosing the right scaling method depends on the model and the data distribution. Decision trees use impurity measures like Gini impurity and entropy to evaluate the quality of splits. These metrics quantify how mixed the classes are in a node, guiding the tree to create purer, more informative splits. Lower impurity means better separation between classes, leading to more accurate predictions. Tree pruning is used to prevent overfitting in decision trees. Pruning removes branches that have little predictive power, simplifying the model and improving its ability to generalize to new data. Common pruning techniques include setting a maximum tree depth or minimum samples per leaf. Mini-batch gradient descent is a popular optimization technique that combines the benefits of batch and stochastic gradient descent. By processing small batches of data at a time, it achieves faster convergence and more stable updates, making it ideal for training large models on modern hardware like GPUs. Stochastic gradient descent, or SGD, updates model weights using one random data point at a time. This makes it very fast and memory efficient, but the updates can be noisy and lead to erratic convergence. Despite this, SGD is widely used for large-scale machine learning tasks due to its speed. Batch gradient descent computes the gradient of the loss function using the entire dataset. While this approach provides stable and accurate updates, it can be very slow and memory-intensive, especially with large datasets. It's best suited for smaller datasets where computational resources are not a limiting factor. Log odds, or the natural logarithm of the odds ratio, is a key concept in logistic regression. It allows the model to fit a linear relationship to the log odds of the target variable, making the coefficients easy to interpret in terms of multiplicative effects on the odds. Imputation is the process of filling in missing values in a dataset. Common strategies include mean, median, or mode imputation, as well as more advanced techniques like KNN or model-based imputation. Choosing the right imputation method can significantly impact model performance, especially when missing data is common. Target encoding is a technique used to handle high cardinality categorical features by replacing each category with the mean of the target variable for that category. This approach keeps the feature matrix dense and avoids the pitfalls of one-hot encoding, such as multicollinearity and excessive sparsity. Another way to handle high cardinality categorical features is to group them into larger, more meaningful categories. For example, zip codes can be grouped into regions or states, reducing the number of unique values and making the model more manageable and interpretable. Reproducibility is crucial in machine learning projects. Setting random seeds like the random state parameter in scikit-learn ensures that experiments can be repeated and results can be verified by different team members. This is especially important in collaborative environments and for regulatory compliance. Data leakage occurs when information from outside the training dataset is used to create the model, leading to overly optimistic performance estimates. Properly separating training and test data and using fit and transform correctly helps prevent leakage and ensures the model's real-world performance is accurately measured. Interpretability is a key consideration in model selection. Linear models are often preferred when transparency is important, as their coefficients can be directly interpreted. Non-parametric models like decision trees offer visual interpretability, while more complex models may require specialized tools to explain their predictions. Summary: understanding the core concepts of machine learning models, from linear regression and logistic regression to KNN and decision trees, is essential for building effective solutions. Knowing the assumptions, strengths, and limitations of each model, as well as best practices for data preprocessing and evaluation, set the foundation for successful machine learning projects. Whether you're working with tabular data, images, or text, these principles will guide you toward robust and interpretable models.